And it gives me great pleasure to give this presentation because my interest in corrosion actually commenced as an undergraduate student when my physical chemistry professor asked me to do some summer research for him. And 3 decades later, I'm still working on corrosion in a variety of aspects. And then my interest with deep water oil and gas exploration occurred when I served as the director of the Applied Research Center, which had an affiliated center called the Center for Energy and Technology of the Americas at Florida International University. And we had received some funding from the Department of Energy to study the injection of carbon dioxide in oil sands. And we also convened a workshop, as was mentioned by Dr. Pereira. Participants at that workshop were from industry, academia, oil companies from Mexico, Brazil, Canada, United States, and representatives of federal agencies. And basically, it was felt that there was a new frontier for oil and gas development, and that was from ultra deep waters. When I speak of ultra deep waters, it means 2,000 meters or greater. It's ultra deep, and anything greater than 500 meters is considered deep water. And so what is corrosion? These are 2 authors who have written textbooks that I have used in all of my preparation and studies of corrosion. Fontana describes corrosion as the deterioration of a material as a result of reaction with its environment. And Uhlig defines it as the destructive attack of a metal by chemical or electrochemical reaction with its environment. It should be noted that corrosion mitigation in industrialized countries represents between 3 to 5% of the gross national product. In the case of the United States, 170 billion per year is spent for corrosion. And of that, about 50% is linked to the oil and gas industries. Now, typical everyday examples of corrosion is simply rusting of an iron pipe or any iron material. And sometimes you can see pitting of steels, like indentations. Now, not to confuse erosion with corrosion, I would like to state that deterioration by purely physical causes is not corrosion, but is considered erosion, wear, or galling. I want to look at the life cycle of materials generally. First, you start with an ore, and I'm going to use aluminum and then go to iron because you're familiar with bauxite in Guyana. Now, aluminum comes from the ore bauxite. The mineral bauxite is treated chemically and is converted to aluminum oxide, which is alumina, a white powder, which is electro-smelted to produce the metal. Typical beer cans are made of aluminum, metal sheets, and the fuselage of airplanes are also made of aluminum. So do engine blocks of the newer cars and wheels. And so you see, you start from a mineral and you go to the metal. But as most of you might recognize, aluminum is used for aircrafts because of the protective nature of the oxide that is formed. So you start with an oxide as the mineral, you go to the metal, which now becomes a metastable state. And then if left to the environment, it goes back to the mineral form. That's the oxide. So the same happens with iron. Iron starts as magnetite or hematite. It goes to a blast furnace, converted into iron, which is alloyed with nickel and chromium or molybdenum, stainless steel. And these steels are in a metastable state. And given any condition where there's oxygen, it will revert back to the oxide. And that's rust that you see in the case of steel. Now, what do I mean by the electrochemical nature of metallic corrosion? Well, you need 4 conditions before corrosion would occur. You need an anodic site. And what I mean by anodic site is where a metal would give up its electron to become an ion, as shown by equation 1. Then you need a cathodic site where that released electron would electrochemically combine with oxygen, water, or the hydrogen ion, as shown by equations 2 and 3 and 4. And then you must have a conductive path, and it must be in the presence of water or an electrolyte. You need to have all 4 of those conditions for corrosion. And at the same token, if you want to control corrosion, you can remove any of those. For example, you can use an inhibitor to cover the surface, so it's now separated from the electrolyte. So those are the basic electrochemical aspects of corrosion. Now, what are the forms of corrosion? You have uniform or general corrosion, where an entire surface is gradually being degraded. You can have galvanic, I will talk about it, dealloying, erosion corrosion, pitting corrosion, crevice corrosion, microbially induced corrosion, intergranular corrosion, and environmentally assisted cracking. And I'll give examples of each of those. This is some research that I did for a wastewater plant that had problems with the chain being subjected to hydrogen sulfide. And as you can see, the chain links had a pin and a bushing. And you have evidence of pitting, which is localized corrosion due to chloride ions, as you could see, indentations on the surface. And it's autocatalytic. It means it's continuous until the holes go right through. Then you can have crevice corrosion. And the crevice is created when the pin goes within the bushing, and there's a formation of concentration cells or stagnant areas where you have a difference in oxygen or a difference in elemental composition. And also you have galvanic corrosion, where you have 2 dissimilar metals in contact in the presence of an electrolyte. So all of these things were occurring here. And these were steel, stainless steels, or 2 different, it turned out there were 2 different types of steel that were put together, and that's why you had galvanic corrosion. Some work that I've also done in corrosion had to do with implants, femoral implants. Femoral stem is shown here in the femoral head. As you could see, there's a crevice here where the head, the femoral stem fits into the head, and that can lead to crevice corrosion. If you have 2 different metals, you can also have galvanic corrosion. And if you have relative minute motion between the head and the stem, you have what is called fretting corrosion. This is another bit of research. One of my PhD students at NASA is working on corrosion. Here you have a stainless pipelines, and you have a carbon steel support, and you have a crevice between the pipeline and the support. And to prevent that is to remove the conductive path by putting a plastic spacer, and that separates. There's no conduction, so you can arrest corrosion there. Well, let's move to corrosion in the oil and gas industry. And what are the 3 reasons for corrosion assessment? And obviously it's finance, economics, and safety. Most of you are familiar with the Blue Horizon, the blowout, and conservation. You don't want downtime in your production. And generally, corrosion must be considered from the basic design phase until you decommission whatever equipment you're using. And corrosion is present in all engineering disciplines. And the reason for that is that crude oil and natural gas have high impurity products, such as carbon dioxide and hydrogen sulfide, and even the formation water. And it's normally accompanied by brine. Wherever you have greater than 4 parts per million of hydrogen sulfide in the extracted gas, it is referred to as sour gas. Now, what are the trends in ultra deep? And as I said, ultra deep water exploration is greater than 2,000 meters. Well, the trend is to deeper wells, greater than 10,000 feet. use of high strength steels, high strength, but yet you need a certain amount of flexibility. And the presence of higher stresses, because you're going about 2 miles down, and the use of lower pH drilling fluids contribute to increased susceptibility of metals to failure. So these are the issues. And as you look at this, the types of casings that are used, you see you can have a production tubing within the production casing, and you have cement protection. And these are 2 types of wells, hydropressured wells and geopressured wells, just to give you an idea of the construction, especially at the bottom, where temperatures can go as high as 95 degrees Celsius. So there are some guidelines to control corrosion, and you must have these guidelines, particularly as you go to depths greater than 5,000 feet. As I said before, bottom hole temperatures can be about 95 degrees Celsius, in which case the casing must be clad with about 3 millimeters of nickel-based alloys. And you would have to have that type of casing all the way until the temperature drops to less than 49 degrees Celsius. Another issue at the bottom of these casings is the pressures. You have up to about 2,000 pounds per square inch, and the partial pressure of carbon dioxide could be above 30 pounds per square inch. As I will describe later, what happens with carbon dioxide. Now, you may say, okay, you have the metal, it's supposed to be stainless steel, so why does it corrode? The reason is, although I said before, metals are in metastable states, which means that you have energy differences in the form of stress gradients or chemical reactivities that are different at different locations across the metal surface. So one site, just maybe a few microns apart, might be anodic, and another one may be cathodic. Anodic means it gives up an electron to become an ion. When it becomes an ion, it means the metal is no longer a solid. It's now a dissolved ion. It's gone into solution. So there's a mass loss. Now, what could also cause concentrations? The differences in concentrations of salts. There are lots of salts in seawater. They have difference amount of deposits, solid or liquid, that could rest on the surface of the metal and change the potentials and cause corrosion to start. And then there are temperature gradients. Like I mentioned, at the bottom, it could be as hot as 95 degrees Celsius. And as you move upwards, the temperature drops. This in itself can set up an anodic and cathodic sites, and corrosion starts. And compositional differences in the metal surface. You may think a metal is compositionally uniform, but that's not the case. You have precipitates, inclusions, also little impurities that can lead to compositional differences, and these lead to corrosion. You want to also consider the properties of seawater. It contains between 2,400 to 4,800 parts per million of sulfate ion. The sulfate ion can lead to microbial-induced corrosion by sulfate-reducing bacteria. Now, seawater, in Guyana's case, it's about 150 miles from the shore, where the pH can be different to the pH close to shore. And so you need to know the pH. And you need to know the salinity, because it changes the corrosion behavior of the metal. Here you can see an example of the corrosion rate of iron in aerated sodium chloride, where you see it increases up to about 3% sodium chloride, and then it falls off. Here you have a relationship between the corrosion rate and brine production. Now, as you explore your wells, you release brine. You have very concentrated brine, and the more brine you have, the greater is the corrosion rate. Here it is shown in mils per year. 1 mil is about 1,000th of an inch. So you can have about 3,000th of an inch as you go from about 10 to 50 barrels productivity of brine. Physically and schematically, let's say you have a metal and you have an anodic site and a cathodic site. Notice this little depression here, because from this electrochemical reaction, you're going from an iron atom to a dissolved ion, dissolved ion, and 2 electrons are released. Now you need a conductive path, so it's on the metal itself, so it flows to another cathodic site, which may be a high stress area. And here, those 2 electrons combined with hydrogen ions, which is basically the dissociation of water, and hydrogen gas is given off. And so that's a corrosion process. And if the temperature increases, that process increases. If the pH increases, the corrosion increases, and so on and so forth. Depending on the type of metal, you could also have a different rate of corrosion. Schematically, here are the different forms of corrosion in a pipeline. General corrosion is where you have an entire surface being removed. Stress corrosion cracking is where you get hydrogen embrittlement and a pressure buildup by hydrogen and it cracks. Crevice corrosion, I described that. And where you have wells, that is also a point of corrosion. Oxygen dissolved in drilling fluids is a major cause of pipeline corrosion. Schematically, in this photograph, rather, you can see the evidence of corrosion. Oil and gas pipelines under sour corrosion is where you have hydrogen sulfide, and it causes this type of failure. Pitting corrosion. When carbon dioxide mixes with water, it forms carbonic acid, and that's the result. When you have pipelines that are connected, here it is threaded, it would fit into the female part of the pipe, and dissolved oxygen in drilling fluid could provoke crevice or pitting corrosion where it is threaded. And this is a common cause of washouts and destruction where you have rubber pipe protectors. This was an example of stress corrosion cracking. So you have to think of these pipelines, you know, as you go down a mile or 2, there's a lot of stress. And hydrogen sulfide with hydrogen embrittlement, you can have this type of stress corrosion cracking. I wanted to show the galvanic series here because different steels behave differently when in contact with each other. So different grades of steel, one can be active as type 410 or type 416. And most of you may be familiar with type 316, which is the common pipes that you have, which is more passive. And if you put these 2 materials together, you can have galvanic corrosion. Here's another example of galvanic corrosion resulting from placing a bronze sea strainer on an aluminum hose. So you have bronze with aluminum, one will become active, one is passive, you have corrosion. You could have microbial-induced corrosion by thiobacillus spheroxidans or Vibrio desulfuricans. Those are a type of bacteria that induce corrosion. Now, how about corrosion mitigation in the oil and gas industry? Now, you can select appropriate materials, different types of steels for different applications. You can use inhibitors. You can use protective coatings, internal and external. And you can use anodic or cathodic protection and adequate corrosion monitoring and inspection. So those are the basic classified ways. Here is a listing of materials commonly used for different applications. All I want to point out here is the amount of chromium and nickel. So you would see chromium in most of these cases here are 20 and above weight percent. And nickel can range from about 2 to 22%. And molybdenum as well. This is a very busy slide, but I just wanted to make the point that different steels have different applications within the oil and gas industry. So where you use carbon steels is not where you're going to use nickel iron or incollies, which are nickel iron chromium alloys. These are used at the wellhead, where I said the temperatures can be as high as 95 degrees. You can't use carbon steel at the wellhead. So this is a guide as to where you can use different steels. And these are some new specialty steels that are also being used in the oil and gas industry in different locations, different applications. Again, you notice chromium content, nickel content, and molybdenum content. Then you can use inhibitors to reduce corrosion. It restricts the rate of the anodic process. It could protect the metal surface. And this way you can slow down the corrosion. Here's a list of recommended inhibitors for the oil and gas applications. It's another busy slide, but it's just for information. You could also use protective coatings. Fusion bond epoxy is very popular. 3-layer olefin and polypropylene, different layers are very popular. This shows the standard thickness of these coatings. Here are some other coatings, and the company that is a great producer of these coatings is in Canada, the Bradero Shaw Company. As Dr. Pereira mentioned, I had the fortune of supervising engineers from Saudi Arabia, the company Aramco, which is one of the largest in the world. And we studied the corrosion behavior of 4 types of coatings: fusion bonded epoxy, modified phenolic, Novalac, amine cured Novalac. And here are some coupons that we got from the manufacturers, and we just wanted to test them because Saudi Arabia had recently discovered offshore oil and gas, and they had sour gas conditions, and they wanted the best coatings. So those 2 students worked on this project. Another way of preventing corrosion is the installation of galvanic anodes, or what we call sacrificial anodes. That means you put more active material, so all of the corrosion occurs on the active material that you don't need, and it protects the pipe. That's basically what it's all about. Another method is the impressed current cathodic protection, where you can suppress equation 1, which is the metal going to iron, by pumping electrons and reversing that reaction so that it stays a metal and it doesn't give off dissolved ions. And so in conclusion, with corrosion, there's a need for rigorous control program and monitoring so that you don't have blowouts like the Deepwater in the Gulf of Mexico. You need to look at the condition of the equipment and record, potential failures or any failure. The properties of the produced fluids must be monitored and known, like the amount of brine, temperatures, pH, all of those factors affect corrosion rates. And of course, corrosion rates must be monitored. And with that, I conclude my presentation and would invite any questions.